Another problem we have with relays are they're fairly slow because you got to, first of all, you got to generate the magnetic field, right? You understand. Then you got to cause the armature to move, and then you got to cause the contacts to close. So relative to what we deal with and a lot of things going on with that today, so there's no way in the world a relay could keep up with an incremental encoder, right? You understand that? So we have these devices called solid state devices. Triacs are used in an AC circuit. So every one of the devices that we're going to be using this semester uses a triac as the output. Unfortunately, triacs will never drop 0 volts. They'll get close, but they'll never drop 0 volts. So in our diagram, we draw a contact, but these guys do not have contacts. The only one that we looked at that has a contact, a physical contact, is the magnetic reed switch. All the other sensors that we're going to use this semester use triacs as their output, because all our sensors are going to be AC sensors.
So triac will never drop 0 volts?
Never drop 0 volts. It's solid state. It's not a closed switch. It is a device that's simulating a contact. It will never, ever drop 0 volts. So we get into a problem in stringing a bunch of these together because the voltage drops add, right? And if we're in a low voltage circuit, like a 26 volt circuit, which is becoming very popular in controls, why is 26 volts becoming AC becoming very popular in controls? So for years and years and years, it was 120 volts, which is what we're using. You're going to still run into a lot in it. Now, if you get into the EDU installation, your control voltage is probably going to be around 26 volts. 26 volts if it's an AC system, and probably 24 volts if it's a DC system. Why? Safety. The NAFTA says that anything over 50 volts is considered to be a lethal push and is potentially deadly. Anything under 50 volts determines how much PPE you can wear. So PPE for anything below 50 volts, PPE is usually just what? Safety glasses, leather gloves when you're working on stuff. Well, not even leather gloves. Under 20, but guys under 50 volts, odds are you're not even going to have to wear leather gloves. Probably going to have to wear long, non clothes that don't burn easily, right? Leather shoes, right? Some companies might require you wear hard hats. Some companies might require you wear ear protection, depends on the noise level in the plant. But guys, so if you went to work for Mercedes, odds are you're going to have to wear ear protection. So when you build cars, that's not quiet, right? So 24 volts, this is where we get into a problem about stringing these guys together, because if they drop 2 volts, you're looking at 26 volts DC, you know, 4 of them right there, that'd drop 8 volts. And now all of a sudden your control relays might not come in anymore. So a lot of these things, and another thing about solid state devices are these solid state sensors. They usually only have one contact. But what can we use that one contact for? Well, bring in a control relay if we need a bunch of contacts, right? And then you're only using, right, to understand that. So control relays, we use a lot of control relays. So it increases our number of contacts. We have SCRs. These are using DC circuits. And then most of them most of your solid state sensors, since they're designed to run. So the main control system that we're using now are programmable logic controllers. There's almost no new installation that you're going to go into where they have all these relays in. They're going to have a PLC, and then there's still going to be relays to handle your high power loads, right? So your PLC will bring in a relay, and the relay will control your high power loads. So we're not doing away with relays. So most of your solid state sensors, your DC sensors, are either going to use an NPN or PNP transistor at their output. An NPN would be for a sinking sensor, and a PNP would be for a sourcing sensor. Y'all understand those things? what's a sinking sensor? Yeah, but what does it provide? So we got two polarities on the DC. We got negative and positive, right? An NPN provides a negative, and a PNP will provide the what? A positive. Makes sense? So an NPN uses a negative as a common, a PNP uses a positive. So just about all your ELC sensors are going to use these capacitors. In fact, I've never seen a sensor that uses this DC that uses it, but I'm sure they're out there. So what we're going to do with ours, this is a, we're going to be using a inductive sensor in this lab. What does inductive sensor detect? Metals, right? So we need some type of metal object like your keys or something like that we'll use. And what happens to these guys is these guys require very little current to operate. They're rated at 220 volts. So these guys will power up through the load. So basically we say in DC that we say in motor control, what's one of our main rules are probably the number of loads. How do we connect loads? We can connect them in parallel or just a one load per line, right? We can have many loads per room. Everybody okay there? So what we got is a solid state sensor. Another problem with solid state sensors is they have to be powered up. They have to be powered to work. So a lot of our solid state sensors, what you're going to see is you're going to see it comes up, and then what's the symbol for a solid state sensor? It's going to be a diamond shape, right? And it's going to have a contact in here, usually normally open. And then it's going to come over, and then our load is going to be right here. And that could be a relay, it could be a solenoid, it could be a light, right? You understand? Then normally, on most of our solid state sensors, we'll put another wire up here, and we'll bring it over to L2. So here's our two power. So here's L1. We got no problem with L1, but if we power it up, then we'll have to run a contact over here. This is going to be 1. And it's going to be brown. This is going to be 3. This is going to be blue. And then your actual signal wire is going to be 4. And it's going to be black. Are we okay? This makes sense? So your power leads are going to be your odd numbers. Now, normally on an AC sensor, 2 and 3 really don't make any difference, right? You understand that? But we want to follow this technique because this is what you'll have to use on DC. Are we okay?
That's 1, 3, 4.
1, 3, 4.
It ain't no 2 of them.
No. What happens is that we got two options on these sensors. We can either have this. I'm gonna draw it like this, which is a single pole, single throw, or we can have this, which is a single pole, double throw. Well, what happens is the normally open is number 4, and it's black. If you have that, if you have a single pole double throw, then number 2 is going to be the normally closed, and this will be white. And that's just the way they came up with it. So your evens are going to be your outputs, and your odds are going to be your power. Does that make sense? Isn't that pretty neat? Now, why they chose to make 4 the normally open and 2 the normally closed, I have no idea. This is just the way it's set up now. We have no option on this, right? So you'll have what we call a 4-wire sensor. So the colors on a 4-wire sensor will be brown, blue, black, and white. That'll be the colors on a 4-wire sensor. On a 3-wire sensor, solid state sensor, they're going to be what? Brown, blue, and black. On a 2-wire solid state sensor, they're going to be brown and blue. I'm sorry. Thank you. Brown and blue. So your Hall effect, the Hall effect is going to be brown and blue, even though it's not solid state. It's a proximity sensor. The inductive sensor that we're using is going to power up through the load. So since it powers up through the load because it requires so little power, the one we're going to be doing is going to be solid state, and it's going to power up through the load. So basically, it's a series circuit, guys, but we don't claim it to be a series circuit. And this is a 2-wire sensor. This guy's going to be brown, and it's going to be 1. This is going to be 3 because it's still considered to be the power lead, and it's going to be what? And this is going to be your inductive sensor, which is a solid state sensor. It's going to drop more voltage than a triac does. So we'll notice that this guy will drop on the average of around 4 volts. Because not only is it running the contact, it's also running the sensing element inside there. So it's running the oscillator, it's running the sense circuit and the flip-flop, it's running everything inside. But when we move to our proximity sensors, it's going to be a 3-wire sensor. Our inductive sensor, which is what we're going to use in lab 1, it's going to be a what? It's going to be an inductive sensor. It's going to be a 2-wire sensor. And y'all saw it last semester. You know, this is basically a repeat of the lab that y'all did last semester. 2-wire sensor. But I think you can see the colors on it. I think you see the brown and blue on it. Yeah, and they should be labeled 1 and 3, right? Not 1 and 2, should be labeled 1 and 3. We okay? Yes or no? So we're going to be dealing with 2. We're going to be dealing with photoelectrics, and we're going to deal with inductive. We don't have a capacitor. Sometimes you might run into an inductive sensor, especially into a low voltage DC circuit where it does not power through the load. It will be a 3-lead sensor on a low voltage circuit, right? On a high voltage, well, not a high 120 volts is not high relative to voltage level. And what is high voltage and what is low voltage? Well, it all depends on where you're working at. So if you work at Alabama Power, you know, usually anything above 10,000 volts is considered to be high voltage. Medium voltage. Anything between like 10,000 and 100,000 is considered to be medium voltage. Anything above 100,000 is considered to be high voltage, right? You understand? In your house, 240 volts is considered to be high voltage, and 120 is considered to be low voltage. In controls, 26 volts would be considered to be low voltage. 120 would be considered to be the high voltage in the control, right? So 120 volts, we can afford to lose 4 volts and not have any problem, as long as we don't string a bunch of these things together, right? You understand that? But in a 26 volt AC circuit, odds are your inductive sensors are going to be 3-wire sensors, because now you can't afford to lose 4 volts, right? You understand that? So ours is going to be 2-wire sensors, because these are 120 volt inductive sensors, and these will be powered up through the load. They're only 2 wires. Load current, everybody okay in there? So this is how much the sensor should draw when it's energized. I don't think y'all did this in motor controls, but here you're actually going to have to break the circuit and measure this current. Everybody okay there, right? So I think I got some alligator clips in my box if you don't have any for your meter leads. Cause you don't wanna, what you wanna do is do what? Break the circuit and clip your meter in there. Don't try to stick your meter up there and hold it, right? Make sure you have it on amps, right? Everybody okay? AC amps. So you're gonna measure the load current. So what's the load current? Yeah, when it's energized, right? Then we have what we call the operating current. This is going to be hard to detect. So the operating current, the operating current should be the current this guy draws all the time, whether it's true or false, right? That makes sense? So your load current is going to be the operating current plus the load, plus the actual true current of the load. So on this one, the load current is going to be the current required to make the solid state operate, and then plus what? The actual current of the load. Does that make sense? Are we okay? That's the operating current. No, that is the load current. The operating current is going to be what it when it's not activated, and you measure that current. So it's going to be down in the milliamps, right? It's going to be really low. So this is just what it causes to fire up the electronics inside the two-wire sensor. So if you were measuring this on a three-wire sensor, you would measure it. You wouldn't measure it here. You would measure it up here in the line that goes to L2. And then we have what they call the holding current.
You said what would measure for operating?
If it's three-wire, if it's a three-wire sensor, then so if it's a three-wire sensor, we would have another lead coming over here and going right there, right? Well, on a three-wire sensor, if I was going to measure the operating current, I would measure it right here. Because that's truly what's causing the sensor to operate, right? That makes sense. That makes sense now?
And on three-wire.
Huh?
And on three-wire.
That's a three-wire, yeah. And then the last current we have is it's not drawing, it's not turning off. Let's see, how do I? Okay, there we go. Nope, still drawing. No, it's not. We're okay. And then the holding current is how much current the load has to draw to keep this thing turned on, right? Makes sense? So solid state devices have what we call the holding current. But once you turn that solid state device on, if you drop it below the holding current, then it's going to do what? It's going to cut off. That means we got to have a load out there that pulls current on. So if my load didn't pull enough current, then what we would do is we'd use our solid state relay to pull in a control relay, and then we'd use the control contacts to run that very low current line. Right? Does that make sense? So what is a control relay? So we have three categories of relays. We have control relays, we have contactors, and we have motor starters. So how would we define a control relay? Nobody knows. Come on, take a guess. How do we define a control relay? That's a relay. That's good. You're right. But that's the definition of a relay. So a contactor would fall into that. We take that definition. A control relay is a relay whose contacts are in the control circuit. They never go into the power circuit. Never. PLCs replace every control relay. because control relays contacts do not go out of the control circuit, right? You understand? A contactor, a contactor is a power relay. It's got big contacts. A contactor has contacts in the power section. It may have what we call auxiliary contacts that can be in the control section, but its power contacts are in the what? In the power section of the control circuit. So most control circuit consists of two parts, right? It consists of a control circuit and a what? Power circuit. And then a motor starter. A motor starter is a contactor that has overload. And overloads detects when a motor pulls over too much current over a certain amount of time, right? So the first lab, proximity switches, this is where we're going to deal with our inductive sensor. Are we okay? It's a 2-wire sensor. It's solid state. It's going to power up through the load. They do talk about capacitive sensors. What advantage does capacitive sensors have over inductive sensors? So what determines what metals a inductive sensor will detect? But that would be one of them, but what type of metals it detects? I wish we had this. The sensors that we did, huh? I hear somebody? Yeah, the more ferrous it is, the better it would detect it, right? So aluminum, it'll detect aluminum, but aluminum is almost no ferrous at all, right? You understand? So aluminum, you're going to have to get real close to it, right? Y'all understand that? But a big chunk of a piece of steel, even though they're the same exact size, and this is what we did up in Tennessee, which was pretty neat. They had a bunch of little old tiny plates, and they were all the same, exactly the same size and the same thickness. And then we moved it up to the inductive sensor to see how close we had to get it. It had in fact, we had a little ruler. We'd put it in a little mount and we'd slide it up until it clicked, and then we would adjust the measurement, which proved to me if you have an inductive sensor that has an analog output, you can use it to figure out what type of metal it is. And I should have known that because you can buy metal detectors now. You can buy metal detectors now, right? That you can switch across the ground. It'll tell you what it is. I mean, it'll tell you what type of metal it is, and it just strictly does it. And then, of course, after that, Bernard was right. After that, then the bigger it is, right? The bigger it is and the thicker it is would determine how close we need to get to it. So it's also the physical size, but also it's the type metal, right? So you'll find out, I think I've got a piece of aluminum. We'll find out on ours, a piece of aluminum, it will detect it, but we'll have to get pretty close. And then we get a pretty good chunk of metal out there, then we're going to be able to do what? Pull it back a little bit. So they had an inductive sensor that had a digital output, and they call them binary, by the way. Pesto calls it binary. Had a binary output, but also had an analog output, and that was really, really neat. And what advantage? So metals, sensing metals. So not only can we sense the metal, we can also, if it's the same type metal, we can see if it's in a certain range, and we can also sense the type metals if we got an analog, right? Or if we got a sensor, if we got a sensitivity adjustment on it, we can sense it. We can adjust it so it will ignore one metal and do what? You pick up another, yeah, at a certain distance. Capacitive, capacitive, we can get these to basically detect any solid. So inductive sensors would be crummy on plastics, right? So this is basically the same thing. We're gonna wire up our circuit. We're gonna hook it up to a light bulb. This is gonna be our inductive. Unfortunately, the symbol that we use for motor controls does not tell us what type of sensor it is. It's basically the same. All we know is if it's a 3-wire sensor, if it's a 2-wire sensor, if it's a 3-wire sensor, or if it's a 4-wire sensor. And I think the only 4-wire sensor we have available is our temperature sensor. So you're gonna wire it up. You're gonna have me check it right. Then what are you gonna have to do? Non-magnetic object, like your finger, right? Then you're gonna measure the voltages. Everybody okay there? Any questions there? Let me give this out to you. It's probably a little better if you actually hold it in your hand. So let's go look it up. So this is lab 1. This is experiment number 1. Sorry about that. This is so I'm inside the procedure steps. I've gone past the discussion, which you're still required to read, right? And that'll answer a lot of y'all's questions. Y'all probably noticed that in motor control. So I'm in step 9. This is after you wire the circuit and you have us check it out. Everybody's okay on wiring the circuit, right? By the way, all the sensors we keep back here on this back shelf, on the second back shelf. We don't want any of the sensors stored out here. We want you, once you get through with them, to put them back on the shelf where you got them from, right? Everybody understand that? In step 9, it says measure the supplied voltage across the proximity switch and across the lane. Okay, so basically you're just going to measure L1 to L2, right? Everybody okay there? Any questions there? With the switch off. Are we okay? Yes or no? Then you're going to measure the voltage across the proximity switch with the load off. Now, is this going to measure the supply voltage or is it going to measure less? Why? Because it has to drop a voltage, right? This guy is powered up through the load. What did I say about what we're going to measure? Probably around 4 volts. But still, that's going to lead to 116 volts out there on the load, right? And most loads are designed to run at their rated voltage plus or minus 10%. So that gives us down to around 97 volts that these guys could run off of. Voltage across the switch with the limits with the switch on. Voltage across the load. Voltage across the load when the switch is off. So this should be equal to this minus this. That's what you should measure there, right? And voltage across the load when it's turned on. We'll have to wait and see on that one. I'm not sure. I just know it's going to be less than 120 volts or whatever. We're using 120 volts. This is going to be your supply voltage. Around here, I think we get around 117 volts. Is that about what we run last semester? Y'all remember? Okay, then we're going to turn it off. You're going to have me check your work. So basically, I'm grading this as we go along, right? You understand that? I think you're going to have me check your work and you turn the power off. Then you're going to, then this is where we got to be careful because here we're going to start measuring more current. Open the circuit between the proximity switch and the load and insert your inline amp. So this is where you need to have these clips, right? You understand that? If you got clips with your meter, they usually come with that. Most people lose those. I have some alligator clip jumpers that you can use. And then you're going to do the same thing. So I'm going to be able to come over and check it, right? And then you're going to put on your PPE, because y'all already know that. Then you're going to measure the low current when it's on, the low current when it's off. The leakage current. The leakage current is going to be what we call the operating current. So that's what you're measuring right there, guys, the operating current. Are we okay? Turn it off. And then you're going to come up. So I'm going to check your work. Then you're going to turn it off, right? And we've got, by the way, we've got tags up here. So we're going to tag out, right, anytime we're working on circuit. Everybody okay there? Using the wiring diagram on the motor plate, connect the motor, three-phase motor, use your trainer with the switch off. So this must be, okay, so this is the circuit we're going to do right here. So we're going to come up here. We're going to do what? By the way, what's nice about the motors that we're using, they're already wired for low voltage. And our transformers are already wired too. We're using the blue trainers. The transformers are already wired. So they got the little metal jumpers on there, so you won't have to jump those out. So this is a circuit you're going to wire. So we're going to use a control relay. And our control relay is going to bring in our motor starter. By the way, there's a little difference between, and I like it this way, for a little different. For one thing, in motor controls, all your devices had the manufacturer's numbers and everything on the device. None of these devices did. But inside the drawer on every trainer, you have a manual, and inside that, it's got every component, and it's got the manufacturer numbers there. Okay, y'all understand that? It's inside the drawer. By the way, we're the only one using these trainers, so if you want to leave, and I don't know if y'all need safety glasses or something like that for your other classes, but if you don't, then you can leave your gloves and safety glasses inside inside that drawer, and that way you won't what? Yeah, you won't forget them. Huh? Yeah. Yeah, because you'd have to borrow Richard, right? And y'all don't know if y'all seen the gloves that Hoyt's got here. Somebody used them last semester. Big old white gloves, yeah. They're probably rated at a couple thousand volts. We're going to wire it, set the ammeter, have your meter settings, put the wire where does it say build the circuit at though? Oh, using the wiring diagram on the motor, connect the motor for 3-phase and used on the trainer. Where does it say for us to build the circuit? Oh, right here. Where does it say build it at? It says have the instructor check your circuit and meter. Oh, connect the control circuit and power circuit shown in figure 13. Okay, which will be what? Which will be this guy right here, right? Everybody okay? And then you're going to do what? After you wired, it's been approved, measure the current in the relay when the load is off. Measure the current when the relay is on, right? Take the inline meter and close the connection between here. Insert an inline ammeter, have the instructor approve. Measure the current of the magnetic motor starter, right? With what? With the motor on and the motor off. Are you okay there? The magnetic motor starter was changed to a larger starter that drew more current, with the current through the proximity switch also increased. That's a good question. And then, of course, these are your questions. Everybody okay? Any questions there? No questions?
How do you put a hand in this?
So where are the inductive proximity sensors at? On the back, right? Okay, let's go ahead and get out the other one. Let's go over this one too. Then we'll be in lab. There must be 3 labs in here. Now I didn't know. Here's 2. All around. Oh, that's it. So if y'all get to 3, I'll just have to go run it off. I'm trying to get started up here. No, that's okay. So here we're going to move to our photoelectric sensor direct scan, which is what we call through the beam. So the person calls it direct scan. So most of the time you'll see on the test when we talk about this guy, I'll use through the beam and then I'll put direct scan. So how does direct scan work? The receiver. So if this guy is not detecting and something, its output will be true, right? Understand? So, I mean, this circuit's going to be outputting 120 volts on our circuit. And then when the device breaks it, it should do what? It should cut it off. Okay, this is not the one we're using. We don't have a blue thing. Okay? And everybody knows how that works, right? These guys are used a lot. We got a bunch of them on. Retroreflective. This is what's nice about these guys is the one that we've got can be used as a retroreflective, and it also can be used as a diffuser. I think this lab is set up for both. And you're going to see the retroreflective. You'll probably run out of wall before that thing stops picking it up between the beams. This is how good those things are. The diffuse, though, you're going to have to get up wall close to it because it depends on the effective. So retroreflector, how does this thing work? We shoot a beam out through a transmitter. So this guy is a transceiver, which means it's not only got the transmitter in it, it's also got the receiver. We shoot a beam out, hits a reflector, a retroreflector. And what is a retroreflector? It does what? Reflects, but it has it's not like a mirror. It actually has a viewable reflection angle, right? You understand? Which is a lot wider than a regular mirror. So these guys, the alignment is not extremely critical. We got a retroreflector up on the moon. You know that?
Okay, that works so good.
And they shoot a beam up there every once in a while. But it don't have to be perfectly aligned, right? Because the retroreflector has a tendency to bounce back from where it came from. And y'all see retroreflectors all the time, like these vests that people wear, you know, when they work on the side of the road. If it was a mirror, it would do what? It would hit angle incidence would be equal to the angle of reflection. But here it wants to reflect back toward the source, right? Only over an angle. So a lot of our white lines have them. They put the little stobs on the interstate, right? The retroreflectors that show you where the lanes are. Huh? Bicycles have them. Motorcycles have them. Some cars have them besides the charge. Oh, really? It must be y'all, it must be you like Chargers. It's pretty cool. I'm more of a Camaro and a Mustang guy. And my wife's been talking about buying one. Yeah. With a Camaro. Yeah, I know. I just don't know how I put my wheelchair in.
I drive.
Yeah, take my wheelchair. Got somewhere I got. I can walk, but I can't walk. So diffuse, are we okay? So what does the fuse do? It's a transceiver, just like the retro reflector. And it's gonna, but it's actually doing more bouncing off the color, so it depends on the collective light. So what's gonna limit this one? Well, distance is one, right? Because it's reflecting back. And what's the other thing? Color. A different color. Cause my shirt is reflected almost no. I would be very poor in a retro, diffuse because I have on a black shirt, right? And black shirts don't reflect almost no light at all, right? I'm saying. So it depends on the color. So we could use these things we could use this to detect a certain color at a certain range, right? Set the sensitivity. So notice these are 3-wire sensors. Oh, he says 2. I thought it was 4. I might be wrong. So I'm probably wrong. I think it is 2. I need to go back and double check that because I've lost your control. But it should be numbered on our sensor, right? So you're going to write that down. Rich was wrong. What day? What time? So 1 would be what color? Brown. Blue. And 2 is going to be violet. So 4 would be white. So this guy here has to be powered up, right? It takes a lot more power than the inductive job. Are we okay? So we'll start off hooking it up to one of our AC lamps. And we're probably going to have to do the same stuff, right? Without using the reflector, place your hand in front of the photoelectric switch so that the lamp turns on. What type of scanning method is used? So if you're letting it reflect off your hand, what type of scanning method is that? It's diffused, right? Then you're going to measure this. I need to run y'all some paper rulers, by the way. Unless some of y'all got a tape measure. Did I require a tape measure in this time? I need to require that. If you got one, that'll be great. If you don't, huh? I don't think huh? What's that? Yeah, because it says inches. Don't say centimeters. And then we're going to have to find something that's black. So what can we use? We can probably use one of these modules right here, right? It's not totally black, but it's probably black now. And then a white sheet of paper, and you're going to see which one would reflect, which one reflects the best. White, yeah, so you should be able to detect that at a further distance, right? Everybody okay? Then you're going to measure the voltages across it, right? And then you're going to measure the watt, current, same thing. And then you're going to hook up basically the same circuit that you did for your inductive sensor. So we're going to use a control relay. Control relay is going to pick up a magnetic motor starter, and we're going to use this to run our motor. So remember, the motor wires directly to the 3-phase power, right? You understand that, right? So remember that through a motor starter. Okay? Yes, no. And then that's it. So that's lab 2, and I didn't run off lab 3. So that gives us 2 labs to do. You should probably take us through the end. Oh, this is lab 3. Guess what you're going to have to do in lab 3? I need to run this off so y'all can play around with this at home. This is where you're gonna have to design your circuit. They're gonna give you a specification of a circuit. This is gonna use a photo, it's gonna use I think retroreflective, I'm not sure. And it's gonna tell you, it's gonna run a car wash. So this is the circuit it wants you to be able to control this right here. So it's gonna have through the beam, right? We'll have to, we can trick this out with a retroreflective, right? You understand that? And when it approaches it, what's it gonna do? It's gonna turn on the light and do stuff like that. All that's in here. You know, what I'll do is I'll go ahead and run this off. 1, 2, 3. I'll just run it off our printer down there. I think I got enough paper down there. And I'll give y'all this out so y'all can start looking at it at home. Okay, guys, y'all got any questions? Y'all got y'all safety glasses and everything? Got your gloves and everything? Right? Got y'all's meter? Okay. All right, guys, y'all take a 10-minute break and come back and we'll go lab.